you type out your code and then press
Not
enter.
really. It's almost 2:30. You need some coffee.
Okay, we're running late, but I'm going to move ahead with the agenda. So I know that the exercises are a lot of fun, but there are more exercises at the end, and if you want, then we can come back and you can finish the first set of exercises. So we'll leave some time at the end for exercises, but really the next stuff that we're going to go over is the exciting stuff that you'll be able to appreciate with the skills that you've built up from earlier today. So there are a couple of things. The last two sort of sections are on this sort of statistical modeling, and then the last one will be about plotting using Ggplot2, and they're both a lot of fun. So ours was made by statisticians originally, so it has a lot of statistical modeling functionality built into it, and it comes with a lot of tests. So everybody's favorite test is the t-test, and it can be applied to pretty much everything. There's so many cases where you have two normal populations and you want to know if their means are the same, and so the t-test is very useful for you in these cases. This is a sort of example of running a t-test. This is just a one sample case, and here you're using R-norm to generate 100 samples from a standard normal, so that's familiar to you. And then this t-test, t.test command runs a t-test for you, and it gives you this output. There's a t-statistic, and you use a freedom and a p-value, and it tells you the alternative hypothesis, which is very important. So the alternative hypothesis, the true mean is not equal to 0, and so the p-value is 0.25, so hopefully you would fail to reject the null hypothesis in this case, which is good because the mean is actually 0. So the null hypothesis is true. If you look at the sort of the components of the object that is returned to you by the t-test, then you can see all of the things which it stores from the computation that you might find useful. So you could find the statistic which was used to generate the p-value. So there's kind of intermediate things, and you can get confidence intervals and an estimate of the mean. So the null value, that's pretty cool. So the point is that the R will not just perform the calculation for you, it will also give you a bunch of artifacts that were created from the calculation of the statistic that might be useful. Okay, so two sample is pretty similar. In the one sample case, you collected one sample data and you're wondering, is the mean equal to 0? T-test, the two sample are where you have two different populations and you're trying to compare whether the means of two different populations are equal to each other. So you can make this less complicated if you just assume that both of the populations have equal variances. Slightly more complicated, where you allow the two populations to have different variances. Or you do a paired t-test, which will be, you just do a one sample t-test on the deltas. So the paired t-test is where you have sort of two sets of data, but there's a natural pairing. So a very common example is like you're measuring how much somebody's weight changes in a month. You measure them at the beginning of the month and the end of the month. And so you have two samples, all the people at the beginning of the month and all the people at the end of the month, but you pair them by each person. So you take, rather than looking at all of those observations, you just take the difference for each person and then do a t-test on those differences. So anyways, this workshop is not primarily about statistics, but R kind of like has all of these kind of classical statistical tests and tools built into it, and all this is very accessible. So here's just the default assumption for the t-test, and it defaults to unequal variances. And it tells you confidence intervals, so if you have two sets of data and you think they're normal, and you want to see if they have the same mean, then you can sort of do these statistics very quickly and easily. And one of the fun things you can do with R is by sampling lots of data, you can see whether or not your p-values are accurate, and you can evaluate whether your confidence intervals are really what they should be by sampling data and running the test many times on samples of data. Okay, so equal variances. So this is the same command, but just with a different option. var.equal equals true. So this is a more restricted assumption. I think it's probably good that the default assumes unequal variances. And then you can also do paired. And in this case, the t-test will just calculate the differences for you. So these are all I think the best thing about these t-tests is mostly just that they're very easy, and it's very easy just to test different hypotheses. But of course, the downside is that it's the same thing, that you're doing multiple hypothesis testing, and you can do data snooping and p-value hacking very easily with R. So, yeah.
Can you explain what the brackets are?
Oh, here.
Yeah.
So in this case, the samples are vectors. So I'll go back. So each one of these things is a vector. Sample 1 is length 30, and this is length 50. Yeah. So it's just taking the first 30 out of 50. Okay, Anova is another crowd pleaser. It's sort of a generalization of the t-test for when you have a bunch of groups, and the null hypothesis is that all of the groups have the same mean, and the alternative is that one of them is, or at least one of them is different from the others. So you're trying to make a better fertilizer, and you have 10 different fertilizers, and you experiment on a lot of plants, and then you measure how much the plants grow, and you wonder, do any of these fertilizers have any effect at all? Is the mean growth of any of the plant subpopulations different from the others? So here again, we're going to sample data. There's not a lot of data, there's only 10 from each one, and they all have different means. So we would hope to reject the null hypothesis in this case. So this is the first time that we'll see the LM function, which is, I think, the first kind of like really powerful part of this that will come out. So here we have lny tilde group, and then the data is just the data that you passed in. So there's also like this function Anova, which will do the same calculations. So Anova is sort of corresponds, it's like the t.test function. It's a function which was designed to do a specific test. But in this case, the test is equivalent to fitting a linear model, where your covariate is the group. And so it's a categorical variable. So one of the great things about R is this formula syntax. And I think we'll see at least a few examples of it. And it's, I think that it's unique to R, and I think that it was designed kind of accidentally, but there's not a lot of sort of competitors for a similar sort of domain-specific language for describing models in this way. So typically, the way that it works is that you put your target variable on the left-hand side, and so this symbol will be a variable which is looked up in your data frame. And then on the right-hand side of the tilde are the explanatory variables. And I forget exactly how many examples we'll see, but the really great expressive power of this tilde model syntax is that you can easily add more explanatory variables with the plus operator. And then you can also add interactions between two variables with the star multiplication operator. And you can do lots of other things too, like you can add or remove the intercept term. You can add stratification into your models. So there's lots of sort of expressive power, which is sort of put into this weird model syntax. But ultimately, at the end of the day, one of the things that it's really buying you is that it's putting together your design matrices. And so if you take, I don't know, an applied statistics course or whatever, you might have to spend time designing matrices with dummy variables and indicators for different levels of categorical variables. Or you know, if you have like higher, like longitudinal data, then you have to sort of like put together these big design matrices. And it's kind of an ugly headache most of the time. And so in a sort of practical sense, that's a big part of what this is expressing, is it's allowing R to build your sort of X matrix, your design matrix, out of the data that you pass in. So that's really nice. Okay, so if you're curious about Anova, there's lots of resources out there. Okay, so now we'll look at an example of linear regression. So this will use the same LM function. LM stands for linear model. And we'll use this prestige data set. So we have a bunch of covariates. We have education. So if we go back and look at the first few lines, education here is a numeric variable. I guess all of these except for type are numeric. Type is the only one that's not numeric. Type is a factor. So average income, percentage of incumbents who are women, prestige score for occupation, Canadian Census occupational code, and the type. So blue collar, professional, etc. So there's a handful of different types of jobs. So here's the linear model with the syntax I mentioned earlier, where we want to try out the model on 3 covariates. So we have 3 explanatory covariates. And we're assigning we're trying to predict prestige, and we're going to look at the output of this variable that we've saved. So this is sort of a model object that R has created. And so it tells us the coefficients. Wonderful. We get the estimates for the intercept and the linear coefficient for each of the explanatory variables that we put in. And then here we look at the names, like all the things that are sort of packaged up inside of the model object. And so this is analogous to what we did with the t-test object. And besides the coefficients, we could also see the residuals, the effects, the rank, all of these great things. Even the QR decomposition of the design matrix. So there's all kinds of great stuff in here that you could pull out and look at if you felt so inclined. And if you ask for the summary, then you get even more information. You can get the standard error coefficients and t statistics for each one. Again, this is with the null hypothesis that each one is 0. So 0 would mean that that explanatory variable had no effect. And p-values. So I don't know how. I don't think that these p-values are typically taken super seriously. It's kind of like a formal statistical test, because you have to think very carefully about like which ones are marginally explanatory and whether the significance corresponds to marginal explanatory power, conditioned on explanatory variables you've already put in. But anyways, it's a nice sort of eyeball way to assess which things are significant. And of course, it's always useful to consider practical significance versus statistical significance. So these things will show kind of statistical significance, and the estimates themselves will show practical significance. And the stars here kind of are as code for how statistically significant these coefficients are. Any questions about these? Yeah.
I have a question about the data equals prestige. If you attach a file, then you don't have to write that, right?
Here?
You have previously, if you attach prestige, use the attach.
Yeah, I don't think we covered the attach command here. But yes, you're right, I
Okay.
think. Yeah.
And then if it is attached and you use data, like data equals, does it mess with it at all? Or?
No, so, well, yes. So data, if you supply data, then then these variables should be columns of this data frame. So you don't have to put in a data argument. If you have vectors floating around, then you can just put in vectors here. And that's essentially what you're doing with attach. Is you're saying, I have a vector called prestige, I have a vector called education, I have a vector called income. So when we say data equals something, what we're really saying is, look up these variables inside this data frame. Rather, I have variables that are defined previously in my code. And the other part of the summary, which is useful, is the residual quantile. So it tells you some information about the residuals. So there are a couple of important things. One is that you hope that the median is close to 0. And you can try to check for a little bit of symmetry between the first quantile and the third quantile, and the min and the max. So this is sort of roughly symmetric, so that's good. So this is another great thing about R's modeling conventions, is that after you fit a model, which in this case is called myreg for my regression, you just pass it into the predict function. And so this kind of this format where you can say predict, and then you pass your model as the first argument, and then the new data set as the second argument, is a very common pattern and applies to pretty much any model that you'll find implemented in R. And so this is a really powerful standard in the R modeling community, and so it's really nice because you don't have to relearn different ways of using each kind of different model. So in new data, this data frame is expected to be mostly the same as the data frame that was used earlier, except for that in this new data, we don't need the response variable, because presumably we're predicting because we don't have the response variable in this new data. So this new data only needs to have the same explanatory variables that were used in the fitting of this model. Okay, and so this is interval predict. So now we get a prediction interval. So we have some confidence about our prediction in this case for the linear model. That's nice.
So for this one, you're basically adding data, and you want to know if it's different than the original?
Yeah. So in this case, we're saying we want to predict the prestige of this occupation, I guess. So like if it requires 13.2 years of education and the income is $12,000, which seems really low. I guess that's monthly income, I forget. And then I think this is like percentage of women who have the occupation or something like that. So this is given some new explanatory variables which I make up. Given a new situation, I want to try to predict the prestige for this combination of covariates. Yeah.
Can you change the prediction interval probability?
I assume so. Yeah, I forget what the option is in this case, but I would hope so, certainly. It's definitely possible, but I don't know what the option is to put it in. So yeah, this is, I would assume that this is the 95% prediction interval. Excellent. So this is similar to what you were asking, Stephen, is this is a confidence interval. Confident is another kind of like standard function for examining models. where you can put in a model, and then this is asking about the coefficient corresponding to this explanatory variable, and then you can put in a level. So maybe I would hope that they have consistent argument names, and that level is the argument name of the other one too. But so this is the 95% confidence interval for the linear regression coefficient for income. And if you just put in your model and the level, then it will just spit out the confidence intervals for each of your coefficients. Okay, and you can look at all these model diagnostic plots. So this is a great way to like impress your friends at parties, maybe. But like, I mean, these. If you're an expert, then you can read these, and in statistics classes we sort of like learn about them. But I mean, at the end of the day, what you're always looking for is some kind of outlier. Are there certain observations that are really tilting the model one way or another, having a highly influential effect on the parameters? Like if you remove a single data point, does it change the outcome of a hypothesis test you're performing? Because that would be a kind of concerning if it did. I don't see any terrible outliers here. The tough question, which R will not answer for you, is what do you do with the outliers? Is it okay to remove them? R can't tell you that. So R will do the easy part of helping you identify the outliers, but ultimately you will have to decide whether or not you can remove them. One of the nice things that I don't think you can really see here is that when there are outliers, R will kind of like automatically label the points on the plot so that you can tell which rows they are. So if there is an outlier, it'll put the row index next to it, so it's easy to go and remove it from your data. Okay, so logistic regression is also very important and really cool and widely useful. So this is for when your observations that you're trying to predict are like Bernoulli random variables. So you're observing like a dichotomous outcome, true or false kind of outcome. Something either did happen, or it didn't. So logistic regression, like machine learning, is used for classification, and it works pretty well most of the time. So let's see, in this data set, MROS. So let's see, labor force participation is factor, number of children, it's going to be integer, age, number of children, life college attendance, log expected wage. Okay, so there are a bunch of explanatory variables, and some of them are factors, and some of them are continuous. So here is an example of using a different modeling function. So instead of LM, we're using GLM, but the format is very similar. So the syntax here on the model is almost exactly the same as for LM, except for this thing on the left-hand side had better be a dichotomous variable. So I would expect some sort of error if you tried to predict something continuous. The family here is binomial logic, so that's not easy to remember, but the point of this is that you can put other link functions in, or if you were doing, say, a different type of GLM, like Poisson regression, then that would just be a different option here. So this GLM function handles all the generalized linear models. So I'm not going to talk about generalized linear models, but probably many of you use them. And the function call is very similar.
Logistic regression is an example of a generalized linear model.
Yes, thank you. Yes, logistic regression is an example of generalized linear model. That's right. So the output is very similar. With logistic regression, rather than the interpretation of the coefficients changes because you don't have the same output and there's a link function. So this is referring to how much a unit increase in K5 affects the log odds ratio of LFT. So it's labor force participation. And so we're trying to predict labor force participation. So K5 has a negative influence. That means that if you have children that are less than 5, it means that you're less likely to participate in labor force. So that seems correct. And age is also negative, but has a much smaller effect. And then this sort of corresponds to the baseline probability of participating in the labor force. So the interpretation of these coefficients changes from the linear model, but other than that, it's pretty analogous. And then this stuff is all related to generalized linear models. And it spits out even more stuff than with linear models. So the generalized, there's just so much interesting names to look at. And again, if you use the summary function on your fitted logistic model, then you can get inferences, standard errors on the coefficients in your logistic regression. Again, it's kind of same as before. You can look at the statistical significance, and you can look at the practical significance. So that's all carries over very easily. Yeah, I'm not going to talk about these. These are the confidence intervals for your coefficients, and you have to exponentiate them. You don't have to exponentiate them, but it makes the interpretation easier. So this is now talking about the odds rather than the log odds. So this is another kind of example of how you manipulate models you've already fit, and this is again like a very standard thing for models in R. Is you can use this update function. If you have a pre-existing model and you just want to sort of change it incrementally by adding or removing some kind of variable, then you can just call the update function and then specify how you want to update the model, and then you put in a different data set. So actually, that's another thing you can do with update is you can pass in a different data set hypothetically. So that's pretty nice, and I mean, you can imagine various reasons why you might want to update your model, but I think that's nice. That models aren't sort of necessarily something that are sort of frozen forever. They can be kind of modified. They're mutable. Okay, here again we're exponentiating so we can get more interpretable confidence intervals for the coefficients. And we can also compare models. So this is for if you're doing some kind of model selection. You have two competing models and you're trying to test which one is more appropriate. There's a statistical way to do that, and there are several different tests that you can execute. Okay, so I don't think that it's, I guess it is time for a break. Okay, yeah, so let's break for 10 minutes, and then when we come back at 3, then we'll dive into Ggplot2. Okay, so it's the beginning of the end. So this is the last sort of lecture component, and then after this we'll have a second set of exercises. And especially during the end, everybody is invited to break out your own data sets, and we can try to help you use R with your own data while we're here. So if you happen to have access to your own data and you'd like to play around with it in R, then you're welcome to do that instead of the exercises at the end. So this last part is my favorite part, and it's sort of a treat at the end because you all stayed for so long, and so now you get to enjoy the sort of the gem. In my eyes. So the last part is about Ggplot2, which is it's an alternative to R's base graphics. So this is something that was developed out of a sort of desire to change how we describe visualization. And it's really an alternative to traditional plotting systems such as the one which is built into R. So you've seen a couple of base graphics today, like the one that was in the hist function that created histograms. But Ggplot is totally different, and the goal for today is mostly for me to convince all of you to begin using Ggplot and ditch everything else that you've ever used. And I really see Ggplot as one of the big motivations to use R as a tool for doing especially like exploratory or interactive data analysis. But one of the sort of downsides of Ggplot2 is that there is a little bit of a learning curve. So I'm going to try to get you as far up the learning curve as I can. So just a little bit about sort of the theory of information visualization. There's some things that we care about that we sort of goals that we would have for any kind of information visualization that we're putting together. So one is efficiency. So this is like how much information is there per unit area of our visualization. We want sort of as much of the area as possible to be used to convey information about our data set. Our data set probably has lots of variables and probably lots of observations, and a lot of visualizations really don't tell you very much about those variables or those cases. Interpretability is another big one. So a lot of charts are kind of surprisingly uninterpretable. So a common example, which Ggplot deliberately excludes, are charts with two y-axes with different units on either side. So those are really misleading and kind of dangerous to use. And there's sort of been raging debates back and forth on the internet for years about whether they should be included in Ggplot, but the answer is pretty definitively no, because there's always a better option.
What's dangerous about them?
You can misinterpret them easily. It's easy to misinterpret them. That's the danger.
How exactly? I mean, what would be an example of that?
I'll defer you to the examples which have come up, but I can point you towards the relevant discussion.
Occasionally there are instances where they are beneficial, though.
So the argument is, I was anticipating so much interest in this. The argument is that even when there is some kind of useful conclusion that you'd want to see using two y-axes, that it would be at least as well communicated using two different graphs, or lining up the data in some other way.
I can think of at least one specific example where there was a case.
Okay, well, I'm gonna have to say let's have a discussion about this afterwards. But I am interested in continuing this line later. But this is the second bullet point on my second slide, so I have a lot of other stuff to get through. So parsimony is another one. We want the simplest plot that communicates what we're trying to say about the data. We don't want to plot with a lot of extra bells and whistles that will distract the viewer from the sort of the point we're trying to convey. And then with respect to these sort of considerations, I think that Ggplot2 lies in a sort of sweet spot that's between sort of reuse flexibility and approachability to make information visualizations that sort of satisfy all of these goals that we have. So most plotting systems that probably most people have used are where you have like some function, and then to change things you put a ton of arguments into your function to add a legend or to add different groupings. And so Ggplot has a totally different approach to how you compose your plots in a way that makes them reusable and much more likely to be efficient and interpretable and parsimonious. So for this section, I'm going to use the diamonds data set. And the first few rows look like this. So caret is numeric, cut and color and clarity are factors. So basically the most confusing part of this is that color is the name of a variable in this data set, and the values of color are letters. So that's really the confusing thing to remember for later. This is Ggplot2 is actually an implementation of a kind of an idea that Leland Wilkinson had. So he kind of has this sort of philosophical, hypothetical grammar graphics, and Ggplot2 sort of carries it out and makes it a real thing that people can use. And it's written by Hadley Wickham, who's a superstar in the R community and has written tons of great packages. Okay, so this is an initial Ggplot2 plot, and it's a histogram. So it's similar to essentially doing a similar thing to the hist function. But So you notice that it's really kind of like two things. You're not just calling a single function. There's a base ggplot function call where I'm putting in the data set, and then I'm doing this weird thing with the price variable, and then I'm saying plus GM histogram. So it seems like we're sort of, this is like more keystrokes to achieve essentially the same effect. And also there's this sort of warning about the number of bins. So I'll talk about why all of this is useful and sort of like worth doing. But the first thing that I'll explain is this AES. So AES stands for aesthetic and is defining explicitly the mapping from variables in your data set to the visual attributes of your visualization. So it's kind of shocking going back from Ggplot to some other system where you sort of have to manually do all of this yourself, where you have to say, I want my different factors to be plotted with different colors, and then you have to go back and make the legend and set the colors again. So the AES is doing what you might have had to do manually in the past. It's saying that you want to put the price variable on the x-axis. So AES has two positional arguments. It's just a normal R function. And the first argument is x, as in the x-axis. So what this is saying in a very sort of concise way is that we want to take the price variable and we want to put it on the x-axis. Of course, this is just saying what data set you're talking about. So this first part is just setting up. You have a data set and you want to put one of the variables on the x-axis. The GM histogram is describing what are you going to do with that, how do you want to display that variable on the x-axis. Maybe there are several different ways that you can do that. And so we'll see examples and variations and sort of how to build on this. But what we'll see more and more of is sort of modularity in adding these things up. So this plus operator is sort of overloaded with these Ggplot things, and you can sort of mash them up in exactly the most natural way that you would expect. And the way that sort of allows, the thing that allows all this is the aesthetic mapping, which really makes it explicit how your variables are being shown on the plot. So this is, apparently, this is a new problem. There used to be an error message that was here, but now there's just a square. So this is one of the reasons that I think it's nice to include Ggplot2 in a workshop like this, is because it's easy to kind of like get hung up on like little differences in Ggplot2, because especially coming from other plotting programs, it's not obvious how to use Ggplot2 to do all the things you're used to doing. And so if you do something like this, then it'll complain, I think, that there are no layers to plot. You're giving it some data set, and then you're not doing anything else. So this is this will give you an error message and won't really tell you how to proceed in a helpful way. Okay, so now this is sort of one step fancier, and we can sort of see how we're beginning to build more. So now this is a histogram, which is faceted by cut. We have a different color for each cut, so it's a little bit small, but there's cut fair, good, very good, premium, I don't know. So, huh?
Ideal.
Ideal? Okay, yeah, I can even, oh yeah, ideal at the bottom, yeah. I guess this legend then is the best. So if this is what I was talking about this morning with, if you wanted to reorder the things in this legend, then you would just reorder the levels of the factor variable cut. So there are a couple of things that, there are a couple of points here that I've done to do this. The first is that I've done something weird, which is I've sort of set up an initial Ggplot object, which I later build on. And so this is sort of already getting at one of the really nice things about Ggplot2, which is being able to assign part of a plot to a variable, and then to be able to continue trying variations on that sort of base plot. So you can really think about these sort of Ggplot objects and the layers as Legos, where you're just really stacking them on top of each other. And this is really nice because for a couple of reasons. One, if you're doing an exploratory analysis, you don't have to type in or repeat all of the different things you put in before, you can sort of say, well, I know I want to look at histograms, and I'm going to be looking at, like, I want to look at several different histograms that are based on this data. And so rather than having to run the hist function a bunch of times, you can start out with something like this, and then try different variations of the histogram function. So basically you're saying, you can put all the variables in here, like this is sort of the domain that I want to explore for the moment, and then each time you look at a graph, you're only changing the sort of the marginal thing which you want to look at differently each time.
So the GEOM underscore histogram, that's a function? That's not a variable you created or anything like that?
That's correct. So
function.
geom, this is, yeah, geom histogram, and yes, that's a function from Ggplot2. And so this is nice for exploratory data analysis, but also for if you're writing a report or you want to make your code reusable, because it makes it much easier to have reusable components of plots. If you're making a plot and it's similar to last quarter's plot, then you don't have to start from scratch and sort of change all of the things. You can start out with the same sort of basic shared components and then only change the parts which are really necessary to change. So here, before when we were calling geom histogram, we called it with no functions. Right here we see another invocation of the aesthetic AES function. So fill here is a visual attribute, and we're mapping cut, which is a variable in our data set, to this visual attribute. So fill is the color of the histogram. It's a little bit confusing at first because color refers to the sort of the border color, whereas fill refers to the inside fill color. So we have one aesthetic mapping defined at the base, and we have another aesthetic mapping defined here. So this is another kind of like interesting thing about the ways you can build up Ggplots, is that you can sort of compose your mappings and play around with different ways of mapping your variables to different aesthetics in your plot. Any questions so far? So here's another cool thing that you can do is, for some reason now apparently I get sick out of the warning message after 2 plots, because now I've set the bin width to something, so I don't have to get the warning. And then here I fasted, so in Ggplot2 terminology, fasting is where you take one plot and then you want to make the same plot for many subsets of your data. And so here I'm faceting, it's facet grid, by cut, and this is a tilde, color. So that means that for every unique combination of the cut factor and the color factor, I want to draw a histogram for that subset. And so again, this is really nice because I didn't have to like start over with a new command kind of like from scratch. I can take like the same sort of basis that I was using before, and then really this part, the facet grid, is the only like new thing that I've marginally added that's giving me all of this expressive power. Okay, so AES is one of the weird things which is kind of confusing at first.
What was that bin width on the last slide?
Oh, the bin width is how wide each bar in the histogram is.
Okay.
So if the bin width is too wide, then you won't really see any of the structure in your data. But if it's too narrow, then it will just look like very noisy, and you'll only be able to see the trees and you'll miss the forest. So AES stands for aesthetic, and it is where you explicitly put in all of your variable names and you say which variable names should correspond to which visual attributes. You can look up all the visual attributes on Ggplot2, so there's a list of the color and the shape, the size and the opacity, all of the visual attributes that you would want are there. So the way that it works is that there are 2 positional arguments, and then the rest of the arguments for visual attributes are named. So the first 2 are x and y. So the position on the x-axis is the first argument, and then the position on the y-axis is the second argument. And then any other visual attributes like color or shape or thickness or whatever are all named arguments after that. So one of the really cool things about VAS is that you can put in functions of your variables. So if you have, these are sort of, I don't know why you would care about these, but if you have like different combinations of your variables you'd like to look at, you can put in little arithmetic statements to be able to plot those really quickly and easily. So that's a nice little feature of the aesthetic. And I think it's especially nice when you can sort of combine different variables and then play around with summaries of multiple variables together. And then the layers are kind of like another weird thing, but as I said before, it's you can really imagine them just as stacking, and it really is a very intuitive thing. So the important thing is that there's an actual concept for it, as opposed to say like in base R, where you can add stuff onto plots that you've made before, but each plot doesn't know about, in base R, there's no sense of the aesthetics, and so you can just sort of like, you're just putting things on a grid. You're just sort of saying like, I want to put a rectangle here, and I want to put a circle shape there. I want to put a legend at these coordinates. But each time you add stuff to your plot, it's not thinking about the aesthetics. So the nice thing about the layers is that you can stack things on top of each other, and Ggplot will, first of all, know how to do that and tell you if you're doing something that's nonsensical, and will sort of use the aesthetics to combine the layers in a meaningful way, whenever possible. So this allows the plots to be built up incrementally, one piece at a time. So it's really great if you're, again, kind of like trying to develop a plot. You can sort of hone in on what kind of plot you want it to be. So the geoms are the geometric objects. We already saw the geom histogram. And so that's saying that you want to draw a histogram of the price data on the x-axis. So there are a bunch of conventions, and I'll talk about more of these later, but the geom names always begin with a geom and an underscore. So scatter plots are something that everybody knows and loves, and they are possible to do in Ggplot2. So the geom in this case is geom underscore point, because you're drawing a point. And so the geoms typically are focusing more on what you're drawing for each datum, rather than calling this a scatter plot. Since scatter plot sort of invokes kind of the entire picture as a whole. So in this case, we have price on the x-axis, and so Ggplot has done this well, and then caret on the y-axis. And we see indeed carets on the y-axis. And then we have geom point. So this is the Ggplot2 version of how you set up a scatter plot. Again, rather than having a special function that will draw a scatter plot, we have a way to set up the aesthetic mapping and then a way of presenting that mapping. Log scales, not a surprising feature, but I think a nice example again of the modularity, where to make the x scale log, you add on a scale, a special Ggplot scale object. And there's a similar sort of scale y, and there are other scale things that do different, that modify the scale in different ways. But again, if you're sort of trying to build this up, then it makes it easy to build on what you have already and then change different aspects of the plot. That's the important thing. So the available scale functions can also handle other variables. So in this case, the price, which is on the x-axis, is a continuous variable, but if you have date times or shapes or colors, they can all handle those things in different ways. Yeah?
Seems like you can do the log with also the function of price. Like
Yes.
Okay.
Yeah, totally. Yeah, so there are multiple ways to skin the cat. And I guess we didn't really talk about date times, but there's a special type, like data type in R for date times. Okay, so here we have assigned some of our are input variables to other visual attributes, in this case, the color and the shape of each point. So this is sort of a muddled rainbow. But looking at the Ggplot2, what we're doing is we're defining a new aesthetic for the geom point, and we're saying we want the color to be mapped to the color. So that seems almost inevitable. And then the shape will correspond to the cut. One of the sort of nice features about Ggplot2 is that it creates legends automatically for you. I've actually heard that the legend creation was the trickiest part of Ggplot2 to implement. But it makes legends for you, and they're pretty good looking by default, and there are ways to modify them and customize them if you want to change their position or, yeah.
Just want to note the subtle point that the color there is spelled with a U. I assume it has to be that way every time.
No, so actually I talked about that, I mentioned that later. So Hadley Wickham is a Kiwi, and so he used the British spelling of these variables. I'm pretty sure that it also supports the American spelling, but I like to use the British version.
Okay.
Because Hadley.
To honor him.
Yes, exactly. So here are sort of like pretty much almost all of the components that you'll see in Ggplot2. So geoms are really like the kind of the bare necessities that we'll need. So they are really what you're usually interested in, which is kind of what do you actually want to draw? What kind of plot do you really want? There are stats, there's a group of stats that do kind of fancier transformations. So there's things like density. So it'll try to sort of like interpolate densities in your data. For example, there's also a stat, I think, for fitting like linear models to your data. So the stats are sort of, often they're kind of coupled with a geom, but they involve some kind of non-trivial statistical computation. They're not just sort of a straightforward rendering like the geoms are. So the scales allow you to sort of tweak the mapping between the data and the aesthetics. So for example, we saw like a scale x log 10. So in that case, the mapping was the price variable to the x-axis, but and then the scale sort of made that a log 10 mapping rather than just an identity mapping. So facets, that was the one that broke up the histogram into sort of a grid under different subpopulations. And there are a couple of different versions of that, but I think you probably get the idea. But there's a couple of different ways to break the data down to subsets, and then whatever plot you had, sort of multiply it. And then the coordinate is something that I don't think that we'll use, but it adjusts the mapping between the two-dimensional plane to the computer screen. So like if you were going to make a pie chart, which I'll discourage you from, the coordinate mapping could be used to get the polar coordinates for your data, and then you would have a pie chart. And I think the coordinate is also used for sometimes in like mapping purposes. It can be used to do different projections of the globe, for example. Okay, so now for this section, I kind of try to this is a sort of more just going through simple examples of Ggplot2, but with the goal of addressing a common visualization problem, which is overplotting. So overplotting is a problem when you have so many data points in some area that you can't really differentiate the structure of the data. There's sort of some censoring because the data is so dense here. We can't really tell how much more points are here versus points that are here because it's all just black. We can only kind of detect variation where it's not very dense. This is a very common issue in visualization, and this sort of sequence is just mostly meant to illustrate different ways that you can use Ggplot2, but it's also sort of fun to think about different ways of dealing with overplotting. So this first one is just to lower the opacity. So in Ggplot2, the opacity is called alpha. Alpha is the name of the visual attribute. And here you'll notice we have no AES call. So this is an argument to g on point, but it's just a constant. So rather than putting alpha equals price, or alpha equals caret, or alpha equals some variable, we're just saying alpha equals a constant. So the rule is, if you want to set your visual attribute to some constant, you can just put it in the argument to the geom. If you want it to be mapped to one of your variables, then you put it inside the aesthetic. So in this case, because we're happy enough just to let it be a constant, we don't need the AES, and this is the result.
So what has it actually done there with the opacity?
This one?
Yeah, in that slide.
So this one, on a scale of, so the opacity runs from 0 to 1, where 0 is invisible and 1 is opaque. So this is making them 90% invisible, or 10% visible.
So when there's many, when they stack upon top of one another, then the blackness increases.
Yes, exactly. Yeah. So like out here, there's sort of like faint gray dots because this is, maybe a singleton point and you can barely see it. Yeah. Okay, so now we're going to go back to the AES. So we're going to try to have some kind of mapping that will determine the opacity, and it'll be a function of the caret. So I've thought about this, and I think that this is actually a pretty bad mapping to use, but I invite all of you to try to find a better one for this data set. But the motivation for having some function is that maybe you could figure out some function where, as it gets into this low price, low caret regime, maybe it makes it more opaque as it approaches the axis, since this is sort of where it seems to be the biggest issue. And so that would sort of like leave the outer points out here relatively dark, and it would still let you see how far the extremes are, but then it would also give you more sensitivity in the very dense region. So anyways, you could play around with different ways of determining opacity like that. But this is just one example of something that you could try.
I'm sorry,
Yeah.
I missed why you, in this case, you put the alpha inside the AES now, whereas the last one you...
Yeah,
just...
good question. It's because now I'm mapping opacity to a function of an input variable. So before it was just constant 0.1. But now I'm saying that I want the opacity to be determined by the caret. And so now for each point, the opacity of the point is going to be 1 over the value of the caret on that diamond.
Yeah, so then I guess I still don't get the aesthetic variable inside of it would be like, what's the difference between inside and outside?
The difference is whether it depends on the variables in your data set. If this depends on the variables in your data set, then it needs to be inside the AES. Back here, it doesn't depend on a variable, it's set to a constant. So that's why it doesn't need the AES.
So the AES function is a function inside the geopoint that I guess takes arguments from your data set and
Yes, and assigns them to the visual properties of your visual tissue. Okay, any other questions? Okay, so another sort of built-in nicety, luxury even, that Ggplot has is this geom jitter. So this is very similar to g on point, except for that it will add some random noise to the placement of the point. So rather than putting a point exactly where it should go, it says, well, let's do like a little bit of randomness away from that. And so the idea is that this might help with overplotting in some cases. In this case, I think that it actually makes the overplotting worse, because now there's kind of like more area which is just dark black. Geom jitter, I think, is most useful for cases in overplotting where you have variables that are rounded, like rounded to integer values, because in that case, all the points would be plotted on precisely the same value, and the geom jitter would sort of spread them out from that single point that they were all rounded to. However, in this case, rounding is not kind of the fundamental reason that the overplotting is bothering us. And so it is not quite as helpful. So this is sort of a fun one. This depends on another separate library called hexbin. But hexbin allows you to use this geom hex, which does hexagonal binning of your data. And so if there's a hexagon where there are any points at all, and then the hexagons are filled in with the color corresponding to how many data points there are in that region. And so with geom hex, we can really see that a huge amount of the diamonds are concentrated in this particular hexagon, which is pretty close to the axis. And we can even see a little bit of sort of lighter blue around here. So the hexbin, I think, is sort of a fun option.
Is that a heat map then?
It's certainly very similar to a heat map. I don't know if it technically qualifies as a heat map because the shapes are not rectangular.
So,
Yeah.
so the count there, that's automatic with geometric text then?
Yes.
If I wanted to change the count, say from, I guess, linear count, because it looks like we're not getting, maybe we don't have enough contrast there between nothing, and can I do like AES, I don't know, log count or something, or is there some way to set that to change?
Yeah, that's a great question. I haven't tried to do that. My guess is that you could do it in a couple different ways. I would look first to see if you could do that with a scale, to modify this with some like scale, a fill scale. But yeah, that's a great question. I think that that's a good idea. Okay. So here's another fun one, and this is an example of using a stat rather than a geom. So this is the stat density 2D. There's also a stat density 1D. But this sort of like finds contours of the density. I think it's kind of a nice contrast to the hexagon binning because it sort of tells you something slightly different about how the sort of the density decays away from the origin. But it's nice that it's sort of very easy to plug it in and compare it with the other methods. Okay, so this is changing gears a little bit. So you can use Ggplot to look at geographical data. This depends on another library, which is the Maps library. The Maps library contains like the boundaries of different geographical entities, including states. And if you get map data state, this gives you the shapes of the, looks like this is just the contiguous United States. Here's an example of using Ggplot without the AES. So it turns out that Ggplot really only requires a data set, and you're allowed to determine all the aesthetics later on. And here we'll do sort of the obvious thing. We have x mapped to the longitude, y to the latitude, and group equals group because each of the boundaries of the boundary points of the states need to be lined up correctly. So if you don't put this group equals group in, then it will sort of bounce around between states because it doesn't know which boundaries correspond to which states. And so this geom is the polygon geom. And so it's sort of a demonstration of how to display polygons that correspond to your data. And so this is how you display arbitrary polygons. And it doesn't seem like it's that bad, I think. And then, so color white. Here, this is maybe the first example we've seen of a mixture of specifying the visual properties, both inside the AES and outside. So here it's outside the AES because it depends on a constant rather than any of the input variables. And the color in this case corresponds to the border colors of the states. Okay. Any questions?
So if you want to do the fill, then you do fill equal.
Right, fill equals green or purple or, yeah, yes. Okay, so Here's another map example. So in this case, I'm using, this is getting the similar data, but from countries around the world. We're using the same geom polygon, same aesthetics, same everything else. But this is just sort of fun, play around with maps. And here's an example. This might be the first example of combining different geoms. So finally, here's some case where we're sort of putting geoms on top of each other. So we start out with the data set of the coordinates of UC Berkeley and UC Irvine. And so we're just defining a data frame with 2 rows and 2 columns. So there's latitude as a column and longitude as a column. Then we have the M here is the state shape data with some aesthetics specifying the longitudes on the x-axis, latitudes on the y-axis, and then we have a geom polygon with group equals group. So here I'm being inconsistent with my previous slide, in part just to illustrate that you can kind of break up your aesthetics between geoms if you want. So the rule is that the ones that come later on, that you add on towards the end of your Ggplot object as you build it up, will sort of be absorbed into your earlier ones. So in this case, geom polygon is using the ones that I defined here. And the aesthetic sort of globs onto each additional thing that you put in. And that's important in this case because when I get to this geom point is sort of inheriting the aesthetics from the base. That's how it knows where to put the points. Because here, even though I say geom point, and I'm using a different data set, it's still using the same aesthetics that I applied at the very beginning. So I start off by saying I'm going to draw a map with longitude on the x-axis and latitude on the y-axis. And then I'm saying on that map I want to put these polygons grouped by state. And then I'm saying on that same map I want to put 2 points from a different data set, but I don't need to specify the aesthetic because it's going to inherit this longitude latitude aesthetic. So another sort of, and then here I have 2 visual attributes of the points. They're going to be red, and their size is going to be 5. And this is sort of illustrating another thing, which is dangerous, but also very empowering, that you can specify different data sets to geoms. So the important thing is that you have to be really careful that your variable names between your data sets match up, because it's not going to work all together if you rename your variables halfway down the road. But if you have a different data set with the same variables that are used in your aesthetics, then you can include that data in geoms after your initial Ggplot.
And is the order in which you append these geoms important? For example, if you put the point, you had appended a point before you appended a polygon, then would you have run into trouble?
Yes, they would have been mostly obscured. So yes, the layers just really go like on top of each other. Yeah, I think in most cases it doesn't matter too much, but occasionally it does. Yeah. Okay, so I didn't cover a lot about Ggplot. It's easy to add labels and legend titles, and of course those are very important and everybody should do it all the time. But it's easy to do, and I'm not going to cover it. Ggsave is the function you can use to save the function to a file, so you can save it as PNG or PDF, or I think even supports GIFs now. So theme BW will create a plot which is suitable for printing. One of the distinctive things about Ggplot2 that perhaps you have recognized is the gray background. And the gray background is meant to be easier to look at on a computer screen. But the intention is that when you print it out, you change the theme using theme BW, for example, so that it has a white background, so that you're not printing gray on all of your paper. So there are different themes. I think that theme BW is the only other one that comes with Ggplot2, but you can get collections of Ggplot2 themes. I think that there's like, there are all kinds of Ggplot2 themes. There's one which is like an XKCD style theme. I think maybe there's like a Scooby-Doo theme, but like you can get like all kinds of different themes, and you just plug them in like this. So you just say like plus whatever plot you had plus a theme, and that changes the sort of the colors of everything. Pie charts, you can do it using the polar coordinate thing, which I mentioned earlier, but I would discourage them because empirically people don't read them very well, and they sort of violate several of the goals that we would have for information visualization. In pretty much every case, it's better to have a bar chart rather than a pie chart. On the internet, you might see people using Ggplot as a function, which is more concise. Ggplot is kind of Ggplot's allowance. It's sort of from the apologist point of view, I guess. But the idea is that people are so used to just having like a plot function. And so if you want to use Ggplot2 as though it were kind of a more traditional plotting library, you can use Ggplot and just like pass tons of different functions and different options into it and get the same kind of style plots out. But I think that using Ggplot is really defeating the purpose of using Ggplot2. Anyways, it's sort of worth being aware of. There are tons of really cool packages that extend Ggplot2. So BD scale is one that I think is really cool. I've never used it, but for scales where you have like dates on the x-axis, it removes weekends and holidays. So if you're looking at like financial data perhaps, then it would sort of automatically clean up your gaps in your data, which would otherwise be a huge pain to remove. Ggalley is I think it has like a bunch of random things in it, but it lets you sort of like line up different Ggplots so that they're aligned with each other on the page. You have several on the same page. XKCD lets you do XKCD style plots. And Ggmap has a bunch of like mapping stuff if you're doing maps, and that's useful. And there are tons of others too. So there's a very rich ecosystem around Ggplot2. And I think that the ecosystem really reflects the modularity of Ggplot2, that so many developers have found ways to extend Ggplot2 in lots of different ways. There's actually a really cool one. I was going to add it, but there's a really cool one that came out recently for putting labels on points, like in scatter plots, but doing it so that the labels like kind of like negatively were sort of separated from each other, so that it's sort of like really smart like label placement for plots, so that they kind of like spread out as much as possible. So there's all kinds of cool stuff that people have done there. So a couple of things with Ggplot. The normal RDocs are fine. So we've been teaching you all day to do like question mark and then like function name. So you can definitely do question mark GM histogram or question mark Ggplot. But for Ggplot, I really would say the online documentation is the way to go. It has an awesome website with tons of examples. I think that it's largely because it's just kind of an inherently visual library. The documentation is really best viewed in a browser where you can see all the pictures. The really big problem with the normal RDocs is they can't show pictures, and so it's just a little bit lackluster. And I sort of already covered these things. The default theme is gray. It's gray background, and we use the British spellings occasionally. Okay, so that's all for Ggplot. So I think we're back kind of like on schedule. So we have a second set of exercises, and the second set of exercises covers has some Ggplot2 stuff, but sort of builds on everything you've learned today. So thanks for listening, and enjoy the exercises. And if you have your data, feel free to get into it, and we'll go around and help you.